This section is on inverse trigonometric functions. Now, a regular trig function takes an angle measure and gives you a triangle ratio, whereas an inverse trig function takes a triangle ratio and gives you an angle measure. And they're necessary for solving all sorts of types of equations where you don't know the angle you need to get it. Now, the first thing about inverse trig functions that we have to note is how to construct them as functions. Normally, if you want to have an inverse function, you switch x and y and solve for y. Now, we can show this in parametric mode on our calculator by putting in our independent variable, which is a t here for y, and then we put in for x sine t. So basically, this is going to, instead of graphing y equals sine x, it's going to graph x equals sine y. And so if we go ahead and graph this, this is our graph of x equals sine y. Now, this is immediately a problem as far as being a function because it does not pass the vertical line test. And if we think about this in terms of a unit circle, it makes sense because if I say sine x equals 1, what's x? You could say pi over 2, you could say 3 pi over 2, you could say 17 pi over 2, you could say negative 111 pi over 2. There's an infinite number of answers, and for us to have a function, we want to just have one answer. And so what we have to do with our inverse trig functions is to restrict their domains. And so what I'm going to do here is I will restrict the domain to go from negative pi over 2 to positive pi over 2. And basically this is going to be quadrant 4 then and quadrant 1, but not quadrant 4 as far as 3 pi over 4 or 3 pi over 2 to 2 pi. It's really negative pi over 2 to pi over 2. And so we take a look at the graph. We're not going to see it. It's going to be pretty small. We just see one little piece of what we had before. And this does actually pass the vertical line test. Right? We can't put a vertical line through this and hit more than one point. So it's a smaller piece of what we saw before, but this allows us to actually have a function. So we have these restrictions. And so what happens is that inverse sine is going to be restricted from quadrants 1 and 4, so negative pi over 2 to positive pi over 2, quadrants 1 and 4. All right, so if we want to find sine theta equals rad 3 over 2, the answer for this equation is pi over 3 plus 2k pi, 2 pi over 3 plus 2k pi, this infinite number of answers. However, if we say alpha is the inverse sine of rad 3 over 2, now we are only looking for that one single answer, which is between negative pi over 2 and positive pi over 2, and this will be first quadrant. Inverse sine same as arc sine, and this occurs at pi over 3. So that is the only answer. There is no other answer. And so again, we are talking about just the first and the fourth quadrant. So while it is true that the sine of 2 pi over 3 is rad 3 over 2, we discount that answer. We discount coterminal answers to here. We only want the one answer of pi over 3. Okay, if we want to find the inverse sine or arc sine of negative 1/2, that's got to be in quadrant 4 because now we're talking about a negative sign. And so we could say 11 pi over 6 because that's in quadrant 4. However, that's not between negative pi over 2 and positive pi over 2 numerically, so you've got to pick negative pi over 6 as your answer. 7 pi over 6 over here, while it's true that sine of 7 pi over 6 is negative 1/2, it does not lie within these quadrants. So that's for sine. Now cosine, we have to restrict it again to get a positive quadrant and a negative quadrant. So we can't use quadrants 1 and 4 because cosine is positive in both of those. So we use quadrants 1 and 2. So our cosine is going to be evaluated for quadrants 1 and 2. That's 0 to pi. So for our cosine of negative 1/2, we got 2 pi over 3 and 4 pi over 3 and all coterminal angles. But our only answer is 2 pi over 3 because that's the one answer between 0 and pi. So first and second quadrant is the only place we look. We look between 0 and pi numerically. Now our tangent, because tangent has a period of pi, theoretically we could either go 0 to pi or we could go negative pi over 2 to pi over 2. Either way, we choose negative pi over 2 to pi over 2. This works nicely because then we don't have to deal with the asymptote in the middle. If you look at y equals tan x graphically, we have these curves, and you get an entire continuous period from negative pi over 2 to positive pi over 2, whereas if you did 0 to pi, you'd have this wing, and then you'd have this wing here. So inverse tan evaluates first and fourth quadrants like inverse sine, negative pi over 2 to pi over 2. And then the sine goes with cosecant, cosine with secant, tangent with cotangent, so on. A little bit of information again about these. You have to be careful when you're talking about the inverse trig functions. If we have cosecant of pi over 4, as we know, that's 1 over sine pi over 4, because cosecant is 1 over sine, which of course is not equal to sine of 4 over pi. It's a little trickier here. Inverse cosine of 2 is equal to the inverse sine of a half, so this time you flip it in here, and that is not equal to 1 over the inverse sine of 2. So just to be clear on that. So let's take a look at these problems over here. Just a few quickies. Inverse or tan theta is equal to negative rad 3. If we're just looking for the specific specific answers from 0 to 2 pi, that's 2 pi over 3 and 5 pi over 3. If you only wanted the answer according to inverse tan of negative rad 3, you'd have to choose negative pi over 3, because that goes with this spot here in quadrant 4. Sine theta is a half. Sine theta is equal to a half over here at pi over 6 and 5 pi over 6. But if we said inverse sine of a half, we would only want pi over 6. Cosine theta of negative 0.26. Well, that's going to be somewhere over here in the second quadrant. So inverse cosine of negative 0.26 will be here. If we wanted to get another solution, we know it's down here. So to get that spot, we would have to do 2 pi minus the inverse cosine of negative 0.26, because this angle here is congruent to this angle here, so that gives us this spot. So this is using inverse trig functions to help us actually solve trig equations for multiple answers. So let me show that again with tan theta is equal to 5. If we have tan theta is equal to 5, well, that'll be up here somewhere and also down here somewhere. So this spot over here is just going to be inverse tan of 5. The calculator will give us the answer between negative pi over 2 and pi over 2, so fourth quadrant, first quadrant. So to get this spot, we have to take the inverse tan of 5, but then also add pi to it, because we've got to go around a half circle to get there. If we wanted to generalize these answers, we could say basically this one plus n pi, and that would include this spot, and all of these for however many periods we would wish. Okay, some more examples we can do with this. The tangent of the arctan of negative 5. These can be tricky because these are not true inverse functions. Tan of arctan of negative 5 is negative 5. Basically, if you take arctan of negative 5, you will be down here somewhere. And then if you take the tangent of that, you're back at negative 5, because the slope of that is negative 5. However, if you do arcsine of sine of 5 pi over 3, sine of pi over 3 is negative rad 3 over 2. Arcsine of negative rad 3 over 2 is negative pi over 3. So you don't get back to 5 pi over 3. They don't purely cancel out. So the arcsine of sine of 5 pi over 3 is negative pi over 3. And then if we want to try cosine of inverse cosine of pi, well, you can't cancel these out and get pi. This doesn't work at all. Inverse cosine of pi does not exist because cosine will never be bigger than 1 or less than negative 1. So you can't take the inverse cosine of pi. That's like saying, where is cosine equal to pi? Well, nowhere. Okay, using right triangles to help us solve things. Tangent of inverse cosine of 2/3. We draw a right triangle. We'll put it in the first quadrant because it's positive. And we say 2's our adjacent, 3's our hypotenuse. Use the Pythagorean theorem in order to get the square root of 5. And then we want to find the tangent of this angle in here. And so we do opposite over adjacent, and we get rad 5 over 2 for our answer. Cosine of inverse sine of negative 3/5. It's negative, so we have to put it in quadrant 4 because inverse cosine is first and fourth, so we put it down here. I'll put negative 3 here for my opposite, 5 for my hypotenuse. If I use the Pythagorean theorem, I get, see, 25 minus 9, so that's rad 16, so that's going to be 4. So then the cosine of this angle is adjacent over hypotenuse, so that's going to be positive 4/5. Okay, this is a little bit trickier. Sine of the arc cosine of 3x. We write 3x as a fraction, and what I'll do is just, you draw a right triangle, don't have to worry about sines and unit circle. Because it's cosine, we put 3x as the adjacent, 1 is the hypotenuse, adjacent over hypotenuse. Use the Pythagorean theorem to get the last side, rad 1 minus 9x squared, and then sine is opposite over hypotenuse, so we have rad 1 minus 9x squared divided by 1, which of course is just rad 1 minus 9x squared. If I want to do the cotangent of arc cosine of 3x, triangle setup is the exact same because it's arc cosine 3x. Cotan is adjacent over hypotenuse, so 3x divided by rad 1 minus 9x squared. Okay, arctan of negative rad 3 over 3, negative pi over 6, because again, it's from negative pi over 2 to pi over 2, and it's negative. We know we're going to be down in this quadrant, negative pi over 6. You can't say 11 pi over 6. It's the same location, but it's not between negative pi over 2 and pi over 2. All right, sine of arcsine of negative 0.2. That actually does cancel out to negative 0.2. Arcsine of negative 0.2 is down here, and if you take the sine of that, it's still that same y value. Here we have arc cosine of cosine 7 pi over 2. The cosine of 7 pi over 2 is 0, and then the arc cosine of 0 is just pi over 2. So we don't get back to where we started. Here we have the cosine of arcsine of 5/13. I did it without putting in a unit circle this time. Doesn't matter too much. Sine is opposite over hypotenuse, so 5 and 13. Pythagorean theorem to get 12. Cosine of this angle is 12 over 13. Cosecant of arctan of negative 5/12. This one I put in a unit circle. Helps me deal with the negative, make sure I don't miss that. So opposite's negative 5, adjacent's 12. And I used the Pythagorean theorem to get the 13 here for the hypotenuse. And then cosecant is going to be hypotenuse over opposite because it's the reciprocal of sine. And so hypotenuse over opposite is negative 13 divided by 5. And finally, one more algebraic one. The secant of the arcsine of x minus 1, you write it as x minus 1 over 1. And so opposite is x minus 1, and hypotenuse is 1. Using the Pythagorean theorem to get this adjacent side, a squared plus x minus 1 squared is 1 squared. We go through and solve for a, and we get rad 2x minus x squared. And so therefore, the secant is hypotenuse over adjacent, so it's 1 divided by rad 2x minus x squared.